Welcome to Chemical Thermodynamics. Today, we'll explore the energy changes that drive chemical reactions and determine their spontaneity. Chemical thermodynamics is the branch of chemistry that deals with energy changes in chemical reactions and the factors that determine whether a reaction will occur spontaneously. We'll cover enthalpy, entropy, Gibbs free energy, and learn how to predict reaction spontaneity using these fundamental concepts. This diagram illustrates how energy flows during chemical reactions, showing reactants transforming to products with associated energy changes. Enthalpy, represented by H, measures the heat content of a system at constant pressure. The change in enthalpy tells us whether a reaction releases or absorbs heat. Delta H equals H products minus H reactants. When delta H is negative, the reaction is exothermic and releases heat. Hess's law states that the total enthalpy change for a reaction is independent of the pathway taken. This allows us to calculate unknown enthalpy changes. For example, if we burn methane, the enthalpy change is negative 890 kilojoules per mole, indicating heat is released. This energy diagram shows an exothermic reaction where the products have lower energy than reactants, resulting in heat release to the surroundings. Entropy, symbolized by S, measures the randomness or disorder in a system. The second law of thermodynamics states that entropy of the universe always increases. Delta S equals S products minus S reactants. Positive delta S means increased disorder, which nature favors. Entropy increases when solids melt to liquids, liquids vaporize to gases, or when the number of particles increases in a reaction. For example, when 1 mole of gas molecules breaks into more gas molecules, entropy increases significantly. When calcium carbonate decomposes to calcium oxide and carbon dioxide, entropy increases because we go from one solid to one solid plus one gas. This diagram compares the ordered arrangement of molecules in a solid with the random, chaotic movement of gas molecules, illustrating the concept of entropy. Gibbs free energy G combines enthalpy and entropy to predict reaction spontaneity. It's the most important thermodynamic function for chemists. Delta G equals delta H minus T times delta S, where T is absolute temperature in Kelvin. When delta G is negative, the reaction is spontaneous and will proceed forward without external energy input. When delta G is positive, the reaction is non-spontaneous and requires energy input to proceed. When delta G equals 0, the system is at equilibrium with no net change occurring. This graph shows how Gibbs free energy changes during a reaction, with the spontaneous direction corresponding to decreasing free energy. Let's solve a numerical problem to see how these concepts work together in practice. Calculate delta G for the formation of ammonia at 298 Kelvin, given the enthalpy and entropy values. The balanced equation shows nitrogen plus 3 hydrogens forming 2 ammonia molecules. Given, delta H equals negative 92.4 kilojoules per mole, and delta S equals negative 199 joules per mole Kelvin. Delta G equals negative 92.4 minus 298 times negative 0.199, which equals negative 92.4 plus 59.3, giving us negative 33.1 kilojoules per mole. Since delta G is negative, this reaction is spontaneous at room temperature, even though entropy decreases. This diagram shows the Haber process where nitrogen and hydrogen molecules combine under pressure to form ammonia, an industrially important spontaneous reaction. Chemical thermodynamics has countless applications in industry, biology, and environmental science. In industry, thermodynamics helps optimize reaction conditions for maximum efficiency and yield in processes like steel production and pharmaceutical synthesis. In biology, thermodynamics explains how cells harvest energy from food and drive non-spontaneous processes like protein synthesis. Environmental applications include understanding pollution remediation and designing more efficient renewable energy systems. Remember the master equation, delta G equals delta H minus T delta S. This single equation predicts reaction spontaneity. If you found this helpful, please like and subscribe for more chemistry content. Practice these concepts with different numerical problems to master thermodynamics. This collage illustrates the wide-ranging applications of thermodynamics, from industrial chemical plants to cellular processes and clean energy technologies.